So, again, good morning, everybody. Today, we are going to learn following objectives. We are going to understand, first of all, the revision of the last lesson, the use of manometer to measure absolute pressure. So, we are going to revise how to use the manometer, and we will have some questions from the past papers. Next objective today is to describe atmospheric pressure according to the change with altitude. So how atmospheric pressure depends on the altitude. We have learned this a little bit yesterday. I will give some examples today. The third objective today, at the end of the lesson, you will be able to understand how we can show the evidence for atmospheric pressure. So you will be able to demonstrate, or you will learn how to demonstrate the existence and the power, the effect of atmospheric pressure. We will have some cool experiments here. And we want to understand how air pressure is utilized in everyday life. Actually, this is the main scope of the lesson. We learn physics, many different subjects, but we want to also explain where they have been used in everyday life. So we are going to see some everyday life applications. So before we start, let's have a quick revision of the manometers. And I want you to have a look at the questions here in the past papers. So everybody will get one sheet. Can you take one and do the rest? We will have some past paper questions, and we are going to look at the problems with manometers. Okay, pay attention to the board now. As we have learned yesterday, this is a manometer, and it's measuring what? Yes? Atmospheric pressure or gas pressure, right? The pressure of any gas. Alright. In the first diagram, I have the manometer, and the liquid inside the U-tube is leveled, is the same level on both sides, at the zero level. What can you say about the pressure on the right and the left side of the manometer? Yes, Sergio? Same, equal, very good. If we have a pressure difference on one side of the manometer, what happens to the other side? It's rising up. So we have the pressure difference. Which side has a higher pressure in this case? Yes. Nuriye?
Left.
Left side. This side has a higher pressure, so the other part is rising. So let's have a look at here again one more time. I have a membrane which is connected with a rubber tube so that it goes through the U-shaped glass tubes of the manometer. I have water, but with food coloring, so it can be seen easily. The levels are the same on both sides, so what can you say about the pressure here and the other side on the membrane here? Same, equal. Very good. Now, I'm just going to press with my finger, so I will apply some force. This will increase the pressure on this side, so you will see the liquid will move on the other side, right? So I'm applying more pressure from left, so the right side liquid is rising up. This is the main principle of manometers. If I lower this rubber, if I lower this membrane down in the water, what do you think we will observe? Yes?
The pressure will increase from that side, so that's, and at the left side the water level will increase up.
Okay, very good. You're right, let's try. And what does this tell you about the water pressure as you go deeper? Look, it's increasing. Very good. The water level, the pressure of water depends on the depth of the water. It also depends on
Density and G.
density and
G.
the gravitational field strength. Okay, so I have the maximum pressure here on this side. As long as the membrane, the manometer stays at the bottom of the tank, we will always have this difference. Alright, now you have some questions on the paper. And which question is this one? I'm not sure. Have a look at this one. I think it is question number 6. Okay, I want you to have a look at number 6 and number which one is it on? Number 6. Yeah, that's number 6. Oh, okay, this one. Have a look at number 6. After that, we are going to solve this one. All right? So you will be in groups throughout the lesson today, and I will ask some questions to the whole group, to one of you in the group. This is the question number 6, right? Batuhan, can you please read?
The diagram shows the level 6 and Y in a liquid manometer when the gas tap is open.
Yes.
What is the pressure of the gas in the cylinder?
What is the pressure of the gas in the cylinder? So, A.
18 cm of liquid below atmospheric pressure. B. 9 cm of liquid below atmospheric pressure. C. 9 cm of liquid above
atmospheric pressure.
D.
And
18 cm of liquid above atmospheric pressure.
okay. Do you have any idea? You can help with your, you can help your friend. You are in the same group. So, do you have an idea? It's either A or B, you say. Okay, you can discuss with your friends. You can sit there. Alright. You are group Alpha, okay? 3 girls here in the front. Alpha. You are Beta. You are Gamma. Alpha, Beta, Gamma.
What is that?
These are the Greek letters. You are Delta, group Delta, and the team Epsilon. All right? We have 5 different teams, and let's see which team will answer this question. Ready? Okay, the Wheel of Fortune tells me Beta will answer this question. All right, Beta.
D.
Theodore.
D.
Okay, Theodore says D. Let's see the question again. This was the question, right? We have 9 centimeters down here, 9 centimeters up in the manometer. You say it's D, so it's 18 centimeters of liquid above the atmospheric pressure. How do you know? How can you explain?
The difference.
The difference, but I see here 9 centimeters, the difference. Huh?
Well, if you add them, you get 18.
If you add them, you get 18 centimeters. What is above, not below? Huh?
Because
Laurent, okay, say yourself. You are
It's going towards Y, it's rolling upwards on the Y.
because this level is higher,
Yes.
goes up. We should look at always the total level difference. So when you have a manometer, you should look at the distance from the top to the bottom. The total height is important, and therefore I have here 18 centimeters. And since gas has a higher pressure than the atmospheric pressure here, it is 18 centimeters above atmospheric pressure, because we have also what? P0 acting from this side. So total pressure here is P0 plus 18 centimeters of this liquid. Mostly it's mercury, so we say 18 centimeters mercury as a pressure. You're right. Okay. You got plus this group from me. First question. Alright, let's go on. I'm just going to now skip the first part, manometers. Okay, you got the idea, I guess. You will solve the other questions as a homework. I mean, this is your homework. All the other questions about the manometers and everything else will be your homework for tomorrow. Okay, I will just leave this one here. You won't need it anymore. And we are going to just move around Google Earth now. Okay, what was our objective at the beginning of the lesson? We said we have to describe how atmospheric pressure is related with altitude. Let's click here. Go to Google Earth. Alright. The first place I want to show you on Google Earth is the lowest altitude on Earth. Where is it? Do you know?
In that hole in the ground, underwater.
Where is it? It's not, I mean, at the surface.
At the surface?
The lowest surface.
Romania.
No.
And
Where? Esther?
like
The name
the
of
lowest altitude.
lowest altitude, it's minus, it's lower than the sea
In
level.
Africa.
In the Atlantic Ocean,
No.
It's not in, I'm not talking about the ocean, okay? It's, the sea level is here, it's lower than sea level.
Uruguay. Being good at
Crater or what?
It's in Africa.
Yeah.
Okay, I think you don't know that. Alright, let's see. It's called Dead Sea. Dead Sea in Jordan.
Jordan.
Dead Sea.
It's water, it's not
Alright,
water.
Dead Sea here, you will see, has, you know, minus 415 meters below the sea level. Dead Sea. I'm just going to draw it here. Minus 415 meters. It's somewhere here in Jordan.
Where's that?
There, it's the lowest place, and the water in that sea, in that place, is very salty that no animal can live there. That's why it's called Dead
Is that in
Sea.
the US?
No, it's not in
Oh
US,
my
it's in Jordan,
God.
as you can see.
Remember,
And it doesn't matter where. Look, what do you think the pressure is? Huh?
it's higher.
It's higher or lower?
Higher.
It's higher.
Higher.
Higher pressure. Okay. It's higher than the one in
Sea level.
sea level. Okay, at sea level, let's say, tell me a country, a kind of place in sea level.
Romania.
In Romania, where is it?
Constanța.
Constanța. Okay, sea level is here. Constanța.
With
Alright.
sea.
We will go up, we will go up to the highest place on earth.
Mount
Mount Everest. Okay, let's go to Mount Everest. It's somewhere here. What's the height of Mount Everest?
8,000 meters or something like 8,000.
Huh?
8,000 and something meters.
8,000.
500.
It should be written somewhere here at the tip.
9.6.
It's the tip here, right?
It says right in the right, more right.
8,000.
No, 9 kilometers.
8,830 meters. That was it. Actually, the top point here. 8,830 meters. This is the sea level, 0. The Mount Everest is the highest place, and the pressure up there should be
Lower.
lower or higher?
Lower.
Lower. Exactly
It's
lower.
closer to the atmosphere.
Yeah.
Because it is closer to the atmosphere, the top layer of the atmosphere. We have less air here. There is one point above the Mount Everest, somewhere very high, which is around 18,000 kilometers. So 18,000 meters.
Where is that?
It's 18 kilometers. This point is called Armstrong limit. And what is this point? Do you know?
When you can breathe.
You cannot survive at this point without a pressure suit. You know why?
Because your lungs and heart will get crushed.
Yeah, because
Kind of. The pressure is very low.
Oh,
And this pilot who discovered the very interesting effect at this limit, at this point, his name was called Armstrong. That's why this name is given to him. At that limit point, the water, the liquid in your body boils. The water will boil at 37 degrees Celsius. So if you don't have a special suit, even tears, your tears will boil away. So you cannot live under normal conditions there. Okay? This is a point where we have a very small pressure. So I just told you the atmospheric pressure. How much was it approximately?
100,000 pascals.
100,000 Pascal. Okay. We can actually measure that and to see exactly how much it is. We are right now somewhere here, right? Around 70 meters from the sea level in Bucharest. Let's say we are here. At Bucharest, it's very close to the pressure at the sea level. And I want to just tell you how we can measure the atmospheric pressure. This is a gas pressure sensor connected to my computer. Has a small hole here, and I can measure the atmospheric pressure by this software. Okay, right now it measures 100,000 kilopascal, almost 100.9, so it's like 101 kilopascal, 101,000 pascals. I can add a syringe to the end, alright, and change the pressure to prove you that it really works. Look, I am now decreasing. Let me try again. Now it is at the normal atmospheric pressure level. When I compress the syringe, what do you think will happen? It will increase because we have less space for the gas, for the particles. They collide with each other more. And the pressure is increasing. Look, 135, 148, 64, and it gets really difficult. Can up to 231. I can compress the gas, so the pressure will increase. We are going to see later the relationship between the volume and the gas pressure according to a law called Boyle's law. We will try to explain this in the next chapter. But I just want to show you that this is a device to measure the gas pressure, and we actually measure here how much? Almost 100.1 kilopascal. Alright.
That's actually 101.
So, what can you say? What can you say about the pressure at Dead Sea? Can you please write some numbers, guess in your paper, and I'm just going to come and ask you. Wait, I'll bring some. Discuss with your friends. The closest one will get the plus in that sense.
450.
For each one separately, write a number and let's see. For this one, for the Dead Sea, okay. I asked the Alpha group, what's it for the Dead Sea? Tell me a number. 6, jump, quick. 300,000. It's too much. It's unfortunately too much. The pressure here is just 107 kilopascal. So it's 7 kilopascal more than the sea level. Alright? Alright. What about, it's just a game, don't worry. Mount Everest, what can you say, Gamma? It decreases, so it should be something?
90.
90. According to the data I have here, it's 33.7 kilopascal. Very low. 1/3 of the pressure we have here.
Zero is.
What about the Armstrong point epsilon? Tell me.
Around 25.
No.
20, you say?
No. I know it's even larger. No, okay, let's put 10.
It's 6.3 kilopascal. You see how small the pressure is up there compared with the one we have here. So that explains me something really interesting actually, because
You can't
Atmosphere.
stay at Mount Everest, Mr.
anyway, yeah, and we actually we need atmosphere to supply oxygen for us, to protect us from the dangerous rays of the sun. But also, there is another thing. We have exactly the right amount of gas with the right amount of layer, the height above us, for us to survive under normal conditions. So the air pressure is right enough for us to live. If it was a bit higher, if we had more air, it would be too much pressure here. If we had less, anyway, everything would be upside down and life would be impossible on Earth. Okay, I just want to skip this part now and show you some small demonstrations about the existence of the air pressure. To do this, I have a glass. Let's keep the questions at the end, okay? I have a glass full of water. Let's put some water here. You already know this maybe. I need a volunteer.
Me.
Enkai? Come. Do you trust science?
Yes.
Enough to risk yourself to get wet?
Your finger.
Sit down here. Alright.
I know that.
Alright. I have... sorry?
It should be full.
Okay, I just put this much.
Don't put on my head.
Alright, over your head. I just put the paper on the glass and just topple it over. Oops. And I just remove this.
If you take out the paper, why does it?
Uh-oh, Enkai.
How long does it stay?
Sorry, Popo.
Just missed. Thank you very much.
Oh God,
It was so close. You know what? The paper got wet and this had a small hole here. I mean, if I let a small hole, the air entered inside and it just fell down. If it was arranged very well, perfectly covered, it would stay for a long time. What does keep the water in here? Yeah.
The pressure on the surface of the paper.
The pressure on the surface of the paper coming from what?
From
Because of air surrounding the glass. But why not the weight of the water and the pressure of the water? It doesn't overcome this pressure. Yeah.
There is like, if you want to get out, nothing is there to replace the place and it becomes void.
So we have a kind of vacuum at the top, right?
Yes.
Because nothing can replace there.
And
So
it pulls it up.
pulls it up. All right. And the atmospheric pressure is very high. It acts at all directions. Atmospheric pressure acts at all directions, and it's much larger than the liquid pressure that we have here. One of the problems we had here, the glass was not full, right? We had too much space here. That's why it fell out. So atmospheric pressure
We're lucky.
is enough to keep the paper there. That is something important. It shows us the existence of the atmospheric pressure. Alright? I'm just going to tell you one more thing about the atmospheric pressure. And in order to do that, crashing cola can. I have a can here. It's empty. We will just put a little bit water here. Not too much. I'm just going to boil the water. It will take some time, so I will start from now. As the water boils, what happens to the state of the water inside?
Become water.
Evaporate.
It will
Evaporate.
Get to evaporate.
evaporation, boiling. There are two different things. Evaporation can happen at all temperatures. Here we have boiling process, so the liquid water will turn into steam, gas. Okay. Let's leave it here. As the steam formed inside, it will push the air out.
So
Out of the
water
can.
will, and because
Ah,
air will come
And-
to
So
all
the can will
sides.
be crashed because of the difference of pressure and the air particles will collide with the can, but there are no air particles inside, so it will crash, right?
Kind of, but this is not enough to show you the crashing of the can. Not by just boiling, it doesn't happen instantly like that. I need to take this can and put it upside down on cold water to observe the crashing. You know why? Because when I put it upside down, the steam inside the can will turn immediately, in a very short time, into water, because it will condense back. And this will produce a partial vacuum inside. Because which one will take more space? The same amount of steam or water, liquid water? Water will take less space. Steam has more space. When you change steam into liquid water, there is a small volume difference. It will take less space. The rest of the volume, the difference will be vacuum. So we will produce a vacuum inside the can by just putting it upside down like that. It should boil a bit more.
It's not working.
Oh yeah, just I need to find it again. Okay, just a bit more, we will wait. And until that time, until that one boils, I want to show you something else. You can actually start working on this problem. The question is, until that one is ready, how much do you think mass we have on our body due to atmospheric pressure? Can you calculate how much mass of air is standing on our shoulders, on our whole body due to the atmospheric pressure? Can we calculate the right amount approximately?
Yes.
Please work on this and try to tell me, using the pressure formula, how much mass does actually stay on our body due to the atmospheric pressure. We want to show you how big the atmospheric pressure is. Which formula should I use?
Pressure equals force over area.
Pressure equals force over area. That's right. Pressure equals force over area. How can I get mass from force?
You can make force equals pressure times area and divide it by 9.807 to get the...
So force is actually the weight here, right?
Yeah.
And from weight, how can I get the mass? I divide it by
9.8.
9.8 G. Alright, so in order to get the force, we need to multiply the pressure with the area. Alright, how much pressure do I have and how much area? The area is given here, as you see. An average human body, a man, has 2 meters square of area.
Pressure.
Yeah, I know the area. The pressure is atmospheric pressure, 100,000 Pascal.
It's much kilograms.
Yeah.
Force is the weight of the air column above us. Alright, how much did you get?
This is
In kilograms, how much is it? How many tons?
20.
20 tons, yes. Mihaila got the right answer, I guess. What about you? 20. Yeah, you multiply that. Okay, 100,000, not 10,000. 100,000. Are you working on the problem? Yes. What about you? Okay. It's not your mass, it's the mass of the air column above us. We're talking about the mass of the air. How much mass of air we have? We have to 100,000 pascal is the air pressure, and your body surface area, 2 meters squared. 20,000. Yes, that's right, that's right. Very good. You got it, you got it. What about you?
I got it.
You got it very well. Very good. Okay, most of the people did well. Let's try to explain. Atmospheric pressure 100,000 pascal. The area is 2 meters squared. Therefore, the force will be 200,000 what? Newton. 200,000 Newton corresponds to 20,000 kilograms. If you divide by 10 simply, right, you will get, as you can see here, 2,000.
Eksik yazdım.
20 tons.
Yes, 20,000 kilograms. So it's around 20 tons. Can you believe that? We have 20 tons of air. Look at here. We have 20 tons of air above us. Because this air is enough to crash a can, why not it doesn't crash us? How can we exist under such great forces attempting to collapse our body? Because if I just try, I hope it will work.
You have
It's
the
very, yeah, it's unfortunately very.
It broke.
You see the can? The dramatic effect of the air pressure. The can collapsed immediately because of the air pressure. Why not our body, under the effect of such a big mass, such a huge force, such a big pressure, can survive? What can keep us safe even though we have such great forces attempting to collapse our body? What can you say? Somebody from a group who didn't say anything. Any ideas? Nuri? No? I think. Okay, Laurent.
The pressure of our blood.
Blood pressure inside is one of the factors. You're right.
And how
Internal pressure inside our body, from the liquid, from the tissues, from the air we have inside. We have air in our lungs, we have blood flowing through our vessels. Everything inside us is balanced by the external factors, the air pressure coming from outside. Inside, outside. If we have the equilibrium, we don't have any problem. If you have a change with the outside pressure, this will be something happening when you go up with the plane, or if you just descend very
Your
fast in
ears
the
go
lift. Your ears. We have a pressure sensor here. Where is the pressure sensor in our body?
Here.
Your ears are like pressure sensors, so you feel the difference. When you go up on the mountains, you feel the difference, and you get a bit dizzy because of that. But under normal conditions, our body, inside pressure of our body is balanced, is in equilibrium with the outside pressure, so we're not crushed like this can. Okay? Good. But we're not the only ones who know physics. Some prairie dogs in nature. Have you ever heard them? What they do?
No.
They do something amazing. These dogs, these prairie dogs, black-tailed prairie dogs, build one entrance of their tunnel underground higher than the one above, higher than the other one. So they have some burrows underground to survive, to live. This is their habitat, living habitat. And they have even different separate rooms for each purpose. They have even a toilet here, right? They have nursery, they have living room, they have different doors to different exits. But what they do is something interesting. As they open a hole and mount at the top of the ground, at the top of the surface, they make one door, let's say, one mount, higher than the other one. There is a level difference between them. What could be the reason for that? Can you guess why? Yes. Esther.
Because if they stay underground, there is a higher pressure, and if they directly go to a lower pressure immediately, maybe it bothers it. They get them dizzy.
Because of pressure, they want to eliminate the effect of pressure difference, maybe you say. Good guess, but this is not the main reason. But it's a good guess. What else? I don't think the pressure difference will be too much in a very short distance here.
They're small.
You have tunnels underground. It should be full of fresh air. They do this to have a natural ventilation system. It's like air conditioning, people. Okay? This is something really interesting and explained in physics by Bernoulli's law, but I'm not going to talk about that. I just want to show you briefly the explanation of this. The higher mounts in the barrows will cause the air flow faster. Air accelerates here. It goes slower relatively to this one. When air flows faster, the pressure here is smaller. When air goes slowly, with respect to this one, the pressure here is high. When you have a pressure difference between two mounts, air flows from high pressure to low pressure, so you have a ventilation system, air current, fresh air always inside the tunnel. Yeah? So, we are cool. They are really cool. They are they are very social animals as well. This is not the only ability that they have. They have very interesting story actually. You can search and read later on the internet. But they utilize the pressure difference, and they have this kind of air conditioning inside their barrels. Okay, let's go on. I have a question for you. You have all tried to draw, you have all in everyday life drink water or other liquids with straws.
Yeah.
What makes us drink easily with straw?
The pull.
Any question? Yes? Somebody who didn't say anything? Yes? You. Seika. You drink like that? How can you do that? How the water is rising up through the straw? Huh? Can it be something with air pressure?
Yes.
What do you do as you... Any idea? You can... Alright. Tell me. Nuriye?
You're decreasing the air pressure in the pipe.
You are decreasing the air pressure inside.
The air pressure outside the pipe, which is on the water, also surface of the water is higher, so the water is...
Like a barometer I told you yesterday, right? It's the same thing. I need two people, two volunteers. This time, okay, you won't get wet. Alright, it's a kind of small
If
competition.
I want to drink water,
You will have an extremely difficult task.
To
You
drink.
will drink water.
I'm thirsty, mister.
Okay,
I'm really thirsty.
who is thirsty?
Me. Eat chocolate before I came.
Whoever drinks the water first, finishes all, will be the winner. Okay,
Like what?
someone,
What will he get?
what you will get?
You get a glass of
Okay.
water.
Get what? Alright, we need the, I cannot decide it. You have many volunteers.
Neither
So let's choose the first person in the team. Delta. Delta. Who said who was raising hand? Oh, you're. And Guy or Jeremy is coming. Alright. And the next person,
Delta again.
No.
Epsilon. Epsilon. Alright.
Mr. Kevin,
Alright.
again, please. I'm thirsty.
Me?
Yes, Marian is coming. Alright. You take the
Şimdi var ya oğlum
Come
tek
over
bardağı lazım.
Start.
Boy versus girl.
Alright, stay in front of your people, in front of your friends. Alright, 3,
Sorry.
2, 1, start! Jeremy is finished!
The match is for the
Maria didn't even get one drop.
I get one.
You got one drop. You couldn't finish.
Why?
How is that possible?
Because boys have less pressure in their mouth.
There must be something wrong with her or with
With the straw.
with the straw.
Why is it happening?
Can you look at the straw once again
That's a hole.
carefully? What does it have? It has some.
Yes, it has some holes.
It has some holes.
It's
You
not
can
fair,
try
it's
it.
a difference.
That wasn't a fair competition. I agree. Okay, you can sit down. Can you please tell me what happened? What happened so that she couldn't drink because of the holes? What happened?
The air.
Yes,
The
Neslia.
water went back outside. It goes.
You are going. It didn't even rise.
Because
Yeah,
there's
because
a
they
air
take
in
the pressure
the
from the
straw,
outside there.
so it cannot come up.
Yeah.
We are trying to lower the pressure inside. If there is no hole, it's easy.
You can cover
You suck the
hole.
air out, the pressure is lower inside, so outside pressure is rising the water through the straw. But if there are some holes, although you are trying to lower the pressure, atmospheric pressure
Go inside.
is entering, air is entering from the holes, and it's always the same pressure inside and outside. So you can't have the pressure difference. Because of that, obviously, you lose. But again, thank you very much for your... You tried, but I did it on purpose to show you the difference between them. Okay, so we have almost finished. How much time we have left?
1 minute.
1 minute. Okay, we finished. I just want to give you an investigation problem, a question for you. We all have ballpoint pens, right? Do you have a ballpoint pen?
Yes.
Alright. In both, not that this one, it's a fountain pen. That's a ballpoint pen. Okay. I had one, I think it's inside. If you open the, like this one, yeah? The ballpoint pen has an ink cartridge here, and this part is left open to air.
Yes.
Do you know why?
So that it
So
can
the
pour.
air can push the ink out.
Air can push the ink always down,
Yes.
so the ink used will be replaced with air always. It's open to the atmospheric pressure.
Yes.
There is a kind of steel rolling ball. It will let the pressure, it will let the ink always down, and you can write. You cannot write upside down with this ballpoint pen. Now the question is, homework for you, together with the questions in the paper, the homework for you. How can you design a pen that could work in space, where
It's a
there is no
motorized
gravity, no air?
It's a motorized pen, Mr.
It is a
It's
space
very
pen.
pressure
In
button.
space pen, right? I want you to investigate how you can make, or how they actually made this, and what is different in space pen with comparison to the normal ballpoint pens.
Mr. It has like,
Because it's a very interesting story actually. I will tell you later next lesson.
it has like a pump and it's pushing.
It has to have something like that. You're right. Okay. Until next time, you are going to finish your homework with the paper, and I'm going to ask you the space pen. All right?